Hello, and welcome to a lecture on optimal illumination of axisymmetric paraboloidal reflectors. My name is Steve Ellingson. First, a quick review of things we've already discussed concerning feeding of reflector antennas. First, a reminder that aperture efficiency is a ratio of effective aperture to physical aperture. Illumination efficiency characterizes the contribution of the feed, and itself is the product of two things: the taper efficiency, which concerns the uniformity of surface illumination, and spillover efficiency, the measure of power wasted in spillover. Optimizing taper and spillover efficiency are mutually exclusive goals. Apparently, it is the illumination efficiency which should be optimized. And then all of this ties back to the issue of f over d, that is focal distance relative to diameter, and feed pattern. So, what is this lecture about? First, a formal mathematical definition of the terms that we used on the previous slide. We'll come up with a mathematical formulation for taper efficiency. We'll come up with a mathematical formulation for spillover efficiency. Then to do an example, and to get a feeling for how these things work, we'll need a feed model. And the feed model we'll employ is called the cosine Q feed model. Then we'll address the concept of edge illumination. This will finally put us in position to discuss how to optimize the illumination efficiency. And then finally we'll summarize, and we'll see how this applies to paraboloidal reflectors generally. So just to remind you, here is a graphical description of the trade-off between taper efficiency and illumination efficiency. Recall, when taper efficiency is high, that means we have good illumination over the reflector, but inevitably leads to spillover, that is wasted power. Whereas if the taper efficiency is low, that means we're wasting power that we could have been applying to the reflector surface, but the benefit is we have low spillover. So these two things are mutually exclusive. Now, illumination efficiency. The definition is power radiated by the feed, which contributes to the formation of a uniform aperture distribution relative to the total power radiated by a feed. And the importance of uniform aperture distribution is that we know that this maximizes directivity. As we've said already, it's useful to characterize the illumination efficiency as a trade-off between taper efficiency and spillover efficiency. In particular, we express it as the product of those two things. So taper efficiency. That's the ratio of power collimated by the reflector surface to the power that could have been collimated by a hypothetical feed which delivers uniform power density to the reflector surface. A reflector antenna with perfect taper efficiency has the same power density at the rim of the reflector as it does in the center of the reflector, which yields the ideal uniform aperture distribution. Obviously, such a feed is difficult to create. Now, this is not necessarily optimal, since in the case of ideal taper efficiency, there must necessarily be a lot of wasted power due to spillover. So, spillover efficiency. Definition: the ratio of power collimated by the reflector surface to the total power radiated by the feed. A reflector antenna with perfect spillover efficiency has a feed which delivers all of the radiated power to the reflector surface with no power radiated outside the rim of the reflector. This is not necessarily optimal, since in that case there must be necessarily a large portion of the reflector surface which is not being used effectively. Taper efficiency. Let's come up with an expression. Here's a way to do this. The taper efficiency could be expressed as the ratio of power density in the direction it's maximum to the power density that we have from a uniformly illuminated aperture, uniform aperture distribution. And we can express power density as a ratio of radiation intensity to distance squared. Now, distance squared cancels out, so we can express taper efficiency as the ratio of the maximum radiation intensity to to the maximum radiation intensity that we would get from a uniformly illuminated aperture. And then also we know that radiation intensity is related to directivity. Specifically, radiation intensity is total power times directivity divided by 4 pi. And in the numerator and denominator, total power and 4 pi cancel out. So taper efficiency is also the ratio of the directivity to the directivity that we would get from a uniformly illuminated aperture. Recall that the directivity of an aperture can be calculated from the fields in the aperture. And this is the expression that we developed in a previous lecture. It's 4 pi over lambda squared times the ratio of these two quantities. One in integration, followed by taking the magnitude squared. Another by taking the magnitude squared first and then integrating over that quantity. For a uniformly excited circular aperture, that is what will appear at the denominator for our expression for taper efficiency. The expression is simple. It's just 4 pi over lambda squared times the physical area of the aperture, which is just pi a squared, where a is simply radius. So we can write the taper efficiency as 1 over the physical aperture, pi a squared, times the ratio of those two integrals. Now, we seek to transform this into an integration over the reflector surface. After all, integration over the aperture is a little bit arbitrary. What we'd like to do is put this in terms of quantities that describe the reflector surface. So here's the idea. The fields in the aperture can be described as the reflected fields in the geo reflection. That can be written as a unit vector times a magnitude in phase, then times e to the minus jk, and z equals 0 because we're in an aperture, and we're assuming this aperture is in the origin of the coordinate system. So here's z, here's rho, and the reflector is out here. So again, unit vector. This is 1 because we're assuming z equals 0, but we could take that aperture anywhere, so we might as well just take it at z equals 0. And then here's the geo reflected field. It's just some constant E naught times the normalized feed pattern multiplied by e to the minus jk 2f. That's the phase factor associated with this distance here. And then divided by 1 over rf prime, which is that distance from the origin where the feed is to the reflector surface. Now, r sub f is focal distance times secant squared of theta sub f divided by 2. This we know from the geometry of paraboloidal reflectors. So we can write the expression as this unit vector times e naught times a normalized feed pattern times e to the minus jk 2f divided by this expression for r sub f. Now we want to integrate over that to get the expression in the numerator for the taper efficiency expression. So here we go. We're integrating over rho from 0 to a, which is the radius of the aperture. V equals 0 to 2 pi. The aperture fields, and then this is simply ds prime in the cylindrical coordinate system. We replace E sub a with the geo reflected field. We note from the geometry of these reflectors that rho prime equals 2 times focal distance times the tangent theta sub f divided by 2. If we take the differential of that in order to get d rho prime, then we get 2f times 1/2 secant squared theta sub f prime divided by 2 times d theta sub f, right? And that simplifies to this expression. So now we have this, and we have this. So putting this all together, this is the expression that we get. It looks rather complicated, but it's going to simplify here. First, we're going to ignore this unit vector. And the reason we're going to do that is we're going to make the assumption that we get perfect cross pol. Now, we don't have the right really to assume that, and most practical feeds will not deliver that. There is a feed that can deliver that. We'll discuss that type of feed in a later lecture. But the reason we're going to ignore it here is because we can account for this effect in a different way. The way will be to define a cross-pole efficiency or a polarization efficiency factor. So we'll keep that effect separate, and we'll simply assume here that the cross-pole is negligible, so we can ignore the unit vector. Also, you'll note we have the same expressions here and here, so we can cancel those out. And then when we pull out constants, or things that are constants with respect to the variables of integration, what we get is a constant unit vector, E naught, 2 times focal distance, e to the minus jk2f, and then an integral over that disc-shaped aperture, normalized feed pattern, tangent theta sub f prime divided by 2, and then d theta sub f d phi prime. So not so bad. Now, one additional thing we're going to do here is we're going to replace the limits rho equals 0 to a with theta sub f equals 0 to theta sub naught. Now remember, this is angle to rim. So integrating from 0 to a is the same as integrating with theta sub f equals 0 to the rim. So that's why we can make that change. And now everything is in terms of theta sub f. We don't have to worry about conversion from rho to theta sub f. We'll take the magnitude squared of that to get the expression in the numerator that we want. So we get magnitude E naught squared 4f squared, and then this whole quantity here. Now the denominator. The denominator of the taper efficiency expression is this. We've already worked out a reasonable way to represent this, so we'll simply make that substitution. Same variables of integration, same thing here, ds prime. We're integrating over the aperture. We make that substitution, it looks like this. So here's the aperture field's magnitude squared, rho prime, d rho prime, and then d phi prime. So we make the same simplifications, the same math applies here, and this is the expression that we get in this case. Magnitude squared of E naught, integral over that aperture disk, the magnitude of the normalized field pattern squared, then we get this trigonometric expression, d theta f prime d phi prime. Now this part here, we can do some work on this. First, we note that this is equal to 2 cosine theta sub f prime divided by 2 sine theta sub f prime divided by 2. And then through a trig identity, this just reduces to sine theta sub f prime. So tremendous amount of simplification there. We can play the same trick with restating the limits of integration. And when the smoke clears, we get this expression for the denominator of our taper efficiency expression. Magnitude E naught squared, and then this integral, which is relatively simple looking. We put this all together, we make the substitutions into the original expression that we came up with, and this is what we get, and this is what we're seeking. This is the taper efficiency for a axisymmetric paraboloidal reflector, expressed now in terms of the radius, the focal distance, the normalized feed pattern. We know those three things, we can now calculate the taper efficiency. Now, spillover efficiency. A convenient way to calculate the spillover efficiency is in terms of beam solid angle. The beam solid angle for the feed, we can say is just omega A, and we'll indicate F here to make it clear we're talking about the feed and not about the overall system. And then in the numerator here, we can just do this calculation again, but not do it over the whole sphere. We'll just do it over the part of the sphere which is intersected by the reflector surface. So the ratio of those two quantities gives us the spillover efficiency. So here's the beam solid angle for the feed. Here is an expression for the beam solid angle of the feed, but now integrating only from theta sub f equals 0 to the rim as opposed to going to pi. Right? And so the denominator is really the same expression, except theta sub f does go to pi. So how do we get the beam solid angle for the feed? Well, quite simply, it's 4 pi divided by the directivity of the feed. So now we have everything we need to get the spillover efficiency. We get it from the directivity of the feed, the normalized feed pattern, and from there it's quite straightforward. The illumination efficiency is now the product of those two quantities, the taper efficiency and the spillover efficiency. We multiply those two expressions that we have already developed, and this is the result. 4 focal length squared divided by physical dimensions times directivity of the feed, and then this integral, which is over the normalized feed pattern. Now note that the radius, A, is 2 times focal length times tangent angle to the rim divided by 2. So we can rewrite this whole mess in this form. So this is the expression for illumination efficiency that we were seeking. It's now illumination efficiency is given in terms of the directivity of the feed, the normalized feed pattern, and the angle to the rim. We know those three things. We can calculate the illumination efficiency.